Great. So thank you everyone for joining us, and we're excited to have Jim Frericks join us today to talk about using classical mechanics reasoning to introduce quantum ideas in your physics classes. So with that, I'll just turn it over to you, Jim.
Okay. I will share my screen here and I'll just start a little bit with telling you a little bit about the project that we're working on. And I'll also tell you a little bit about some more of the uh, approaches that you can use at the end. We're going to actually go through one of the first things that you can do with a class during the time we have together today. It is going to be hands-on, so I'm going to hope that you'll be able to work on, we'll have some worksheets and things. They're going to be available electronically, and I hope that you'll be able to work with them. Um, if you need time to print them out, I'm sure there's plenty of time to do that if that's something that you would like to do. The idea behind this is that I've always found it very strange that when we go to quantum mechanics, we kind of tell our students after they've spent 1 or more years studying classical mechanics, essentially everything that you learned is not relevant. Quantum mechanics is totally different, and here's what it is. And it looks nothing like classical mechanics and classical reasoning. And so don't think about any of that when you're working in quantum mechanics. Um, and I think that's throwing away a vast resource that we have, which is that our students have been spending a lot of time uh, understanding classical ideas. And there actually are very deep and interesting connections between classical mechanics and quantum mechanics. And I'm working on a project now where we're working on both a textbook that will introduce quantum mechanics in this fashion. And also, we're trying to develop a lot of additional educational materials that go with the textbook so that it becomes something that's easier to use. It's envisioned to be used in a sophomore level modern physics class, but some of the things can just be taken and used in introductory physics toward the end if you want to introduce quantum mechanics ideas. So that's kind of the rationale for what we're doing. Also, this is a relatively small group. If at any time something is confusing or you want to ask a question, please feel free to go ahead and do that. It doesn't bother me one bit to be interrupted in this. So, in fact, I encourage it. So, I welcome you to do that. Okay. So, as I said, my goal is to find ways to connect classical ideas to quantum ideas as much as possible and carefully show where they differ because they are not the same. And I think this is the best way that you can introduce quantum ideas when you're doing it earlier in the curriculum. Trying to jump into Schrodinger's equation right from the start is usually not the best thing to do with younger students. Um, the philosophy behind this is that it's the power for ideas, not the advanced math, that is important. And I'm going to show this to you in discussing two different aspects of photons. And the first thing we're going to start with is the photoelectric effect. Um, and the first thing that you encounter when you're trying to deal with anything in quantum mechanics is a question that we often don't ask, but we really should, which is individual quanta are too small to see by the eye. So how do we actually do experiments on them? So I'm going to describe as a model for electrons in a metal where they are held in a harmonic trap. I mean, frankly, if you were back in the 1900s, you have no idea what's holding the electrons inside a metal. And because every potential at the bottom looks like a harmonic oscillator, thinking about the trap as being something like a harmonic oscillator is actually not a bad idea. In fact, this is the model that Lorentz, the famous guy of the Lorentz transformation, He developed a whole theory for models based on electrons in harmonic oscillator traps. And if you think about it, it's kind of related to what Planck said when he was solving blackbody radiation, where he said the black body has some set of oscillators in it that oscillate and radiate electromagnetic radiation. So this notion that metals might be able to be described by harmonic oscillators trapping electrons is a very reasonable approach. Of course, they're not harmonic oscillators up to very high energies because eventually the electrons can escape from the metal. So if we're going to use that analogy, the first thing you want to focus on is the concept of resonance. And if we were to drive our electrons with a weak electric field, then we can only get a high amplitude if we drive them on resonance. So here's a cute little video that, oh, I'm not sure. I might have to share again. I don't think I shared my computer share sound. Otherwise, this isn't going to work very well. Let's try that again. Okay. So this is a cute little video showing if you don't drive on resonance, you don't go anywhere. But now if you decide to drive on resonance, you can start to build up an amplitude.
No, that's a little hot.
And you can get the amplitude up to be pretty high if you keep just driving on resonance. And it doesn't take very big pushes, even small pushes. And the idea is then that you can resonantly excite electrons out of these potential wells. And that could be a theory for how electrons are emitted from a metal. So if we were to use that, then a couple of questions arise. Is it all the same trap, so there's one resonance frequency, or are there many resonance frequencies? Again, if you use the Planck ideas of blackbody radiation, you would come to the notion that maybe there are lots of different kinds of resonant frequencies. Then because this is a resonance drive, would you expect that it takes more time to be emitted from a low amplitude than a high amplitude field? And the answer to that is, of course, yes, because it will take more time to build up a large amplitude if the idea is that the electron has to have an amplitude of motion, say on the order of a nanometer, to be emitted from the metal when the electron is near the surface. Then another question, which is a very important one, is how do we detect the emitted photons? This goes into the standard way that the photoelectric effect experiment is described. And then there are other questions that are important, like what happens if we change the color of the light, if we have the capacity to change that. In the early experiments on the photoelectric effect, they actually were not able to change the color of the light because they only had broadband light sources. But this now leads to a number of classical predictions for resonant excitation. The first one is that the light must have a frequency that matches essentially the frequency, or you can think of it in terms of energy, matches the energy, the bound energy of the electron. So, so you have to have resonance matching. And because the trapping frequencies can't go all the way to zero because electrons don't just spontaneously come out of metals, there must be a minimum frequency. And so unlike what most textbooks say, the moment you decide you want to look at something as a resonant drive to describe photoemission, you then are required to think about there being a minimum frequency before electrons will come out. So although a lot of books will say classical physics cannot predict a minimum frequency before electrons are emitted, that's patently wrong. Classical mechanics is actually quite capable of doing that. Now, when we emit the electrons on resonance, once they can get out, they go out. So the kinetic energy of the electrons should depend only very weakly on the intensity and the frequency of light. It should be essentially the same for every driving that I'm doing, because once they can be emitted, they get emitted with essentially very, very small kinetic energy. Once they reach the threshold, they'll be emitted. So this is, again, a testable thing that you can interrogate with your ideas about the photoelectric effect and trying to describe it classically. Another prediction you would make is that low amplitude light will take longer to first emit electrons because the resonance takes time to build up. And we should see some materials dependence because the minimal frequency for resonance matching could be different for different metals. So there's a number of things that actually are the things that occur in the photoelectric effect that you can describe classically, but there are other things that are not apparent in the experiment. So what is actually seen? Low frequency light emits no electrons regardless of the intensity. This is consistent with the classical description. Electrons are emitted immediately with no delay when the frequency is high enough. This is only consistent with the classical description if the time scale for the resonance to build up is really small, like less than a nanosecond or something like that. Otherwise, this would be in contrast with the classical result. The threshold frequency varies with the metal used. This can also be described classically. And then finally, higher intensity light emits more electrons, and their maximal kinetic energy is independent of the intensity, but depends on the frequency of light. This is consistent with the classical theory, except for the kinetic energy depending on the frequency of light. That you wouldn't get with a threshold excitation. But I hope you can see that the situation is much more nuanced than the way textbooks tend to lay it out for the photoelectric effect. And I think by relying on or even using as a foundation these classical ideas with your students, it helps make them understand a bit better what to expect from a photoelectric effect. Okay, so what I would like to do, we have two things here. I'm going to actually put them in the chat as well. Let me see if I can actually do that. I just have to copy. Whoops. I think I have to do this, and then I can copy in the chat. Oops, I think I did that twice. I think it'll still work. Okay, and then the second one. So how many of you have used the FET on the photoelectric effect? What these two links are, one is a worksheet, and the other is a link to the FET simulation. And what I would like to do, I'm going to stop sharing. What I would like to do is have us break up into breakout rooms. It might be, I don't know how many are going to be going in the breakout rooms, but I don't think we need too many. No more than 3 people per breakout room should be fine. And I will come through the breakout rooms, make sure that you're able to get started. We'll run the FET simulation, and we will take a look at these worksheets and try to go through them. This is a way that you can understand what are the quantum effects in the photoelectric effect and what are the things that can actually be described classically. The FET simulation does not do a great job about explaining these different ideas, but as I just showed you, the worksheet will go through and show you in detail how you can reconcile classical reasoning and where it fails when it comes into the photoelectric effect. And then we'll come back and we'll talk about what it means. Are there any questions from anyone? If not, why don't we go ahead and I'll come around and visit the different.
All right, so I'm going to open all the rooms. You should be able to access the rooms with a link that says, join room here. And I'll see you all back here when you're when you're ready, Jim.
Yeah, I will go into the different rooms and see that everyone has gotten started. I just want to make sure I have a copy of the worksheet available as well. So I'm going to just go ahead and start rotating through the rooms and make sure everyone has gotten started and then talk to them about things. And I think at the absolute latest around 150, but I'll see how well they're doing with the materials.
Yeah, I'll
And
wait till you come back and
yeah, well, I'll be coming back and forth, so I'm gonna
yeah.
because I think I have to come back here to visit another room.
Sometimes you do and sometimes you don't. I haven't figured out what the pattern is. So
Okay, all right. Well, I'm gonna go to the first room.
all right, sounds good.
So we can do a little bit of a debrief. People can say what they thought about things, how they like the simulation. I have nothing to do with the simulation. We're just using it. The worksheets are our stuff. But I think it can give you a good sense of how the experiment works. And then the question of how you interpret it, which is also talked about a little bit on the worksheet, but we can also talk about a little bit here before going to the next stage, is also quite important as well. Did anyone have any thoughts they wanted to share?
Okay, I'll jump in to break the ice here. So I wasn't in a breakout room, so I didn't get a chance to actually see the worksheets, but I know that I have used the photoelectric effect FET simulation and to introduce quantum mechanics to my students and the idea of the photons as energy packets, and was rather surprised at how difficult students found applying ideas of conservation of energy and um, that kind of thing to the simulation, and needed a lot of scaffolding um, to get them to think through what was going on. So I'm curious to
I
hear
think
your
another
thoughts.
thing that really causes trouble is getting them to understand what changing the voltage does.
Yes, yes, there. It brings
They're,
out a lot of poorly understood concepts from classical ideas.
and I kind of view this as a really nice opportunity to try to strengthen those ideas when you're talking about it. Other thoughts that people have? So
Just,
one, go
I'm
ahead.
sorry.
Yeah,
Just for
go ahead.
me, having 100% high school girls in a private school, I've used PhET simulations in the past. So a big thing for me with the girls, without getting them too frustrated, is telling them what the end product, what is the target that we need. So stopping voltage is a good one. Maybe I will need something like an animated GIF or something like that to show them like this is what you want to achieve. Just let me know what the voltage is. And then like for, again, I'm flexing these muscles after a long time. All right. So voltage is the potential though, right? Amperes is the actual measurement.
So what the voltage does is the voltage creates an electric field. So essentially what happens is from the emitter plate, you have electrons that are emitted, but in many different directions, not all straight towards the collector plate, even though the FET shows them pretty much all going straight toward the collector plate. Um, the uh, they actually come out in all different kinds of angles. So if I'm at 0 voltage, I don't get them all. Some will miss the plate because they're coming out at the wrong direction. But if I make the voltage more and more positive, eventually I'll collect all of them. And then if I make it higher still, there's no more to collect. I already have them all. That's why the voltage saturates at high potential. Then the reason why it goes to, why the current, that's why the current saturates at high potential. The reason why the current goes to 0 is if I repel the electrons, so much so that even with the kinetic energy they have, they don't have enough energy to go through this electric field to be able to get to the collector plate. I'll get no current. And those are like the main sort of physical ideas that you need to understand how the experiment works. And that's all based on classical physics. Then the quantum comes in where you learn that as you change the intensity, the stopping voltage doesn't change. Because the most naive classical approach would say that changing the intensity, I'm giving more energy, so more kinetic energy should come out. And that means the stopping voltage should become more negative, but it doesn't. And changing the color does. That's also not something that is so easy to reconcile with any classical picture, even the one that I talked about with resonance, because because in the classical viewpoint, where you can get that you need a minimum frequency in order to emit, the electrons all get emitted with essentially the same kinetic energy, and it's a very low kinetic energy. So the stopping voltage would be very close to 0, and changing the frequency would not affect it. So you finally can get to the point that you learn that the simple classical description does not work. Now, the next point I'm going to say is something that probably is not something you want to say with high school students. But if you have, especially if you're teaching sophomores, I think it is perfectly fine to do that. Even though every single textbook says photoelectric effect tells you that light is made out of photons, it actually does not. Because what it actually tells you is that the metal is quantum. Because you can actually do a simulation. Now I'm talking not about a PhET simulation, I mean calculation, but with the computer, where you just put in a classical light field on quantum electrons and you get all of the behavior of the photoelectric effect. So while it's very suggestive that light is made out of photons, it actually doesn't prove that light is made out of photons. So that's actually a very subtle point. It's an advanced idea. I don't think it's appropriate for high school students, but it leads into the next thing that I want to do, which is how do I really establish that there are photons? And that's the thing that I want to talk about next. But before I jump into that, just want to see if there are any more questions that people have. If not, I'm going to go ahead. I'm going to share again. And here's where we get to stuff that you're not going to see in most modern physics textbooks. I haven't actually gone through every one of them to see whether there's any that actually does it, but most do not do what we're going to do now, which is talk about what a single photon source is and how you detect and verify that you have single photon light. So the first question, that we always grapple with when we're talking about quantum mechanics is a photon a wave or a particle? This often goes by the name of duality. There's a rich history to this. Newton first proposed that it was a particle because light casts sharp shadows, and because Newton was such a hero of physics, no one wanted to question him. So it wasn't until the 1800s that Thomas Young showed it had wave properties. And even though I think it was Fresnel came up with a theory that properly described it, Poincaré was vehemently opposed to this, and Poincaré figured out that if it's a wave, If you shine light on a disk, in the middle of the shadow, you'll see a bright spot. But if it's particles, you won't. And Francois Arago did the experiment, saw the bright spot, and that's what brought in the wave theory. It's actually not Thomas Young. Thomas Young got the discussion started, but it's the spot of Arago that convinced the elite scientists of the time that light is a wave. And then, of course, you have Einstein showing that light may also have a particle nature to it. So I've been talking all about this stuff with the photoelectric effect. What we haven't talked about are the different kinds of light sources that you might have. So classical light comes in many different ways. There are thermal sources of light, which is black body radiation. That is the incandescent light bulb, which is becoming rarer and rarer to find. Of course, the sun is a nice example of a black body radiation. You also have stimulated emission sources like light-emitting diodes and lasers. Many people are surprised to learn these are also classical light sources. They're not quantum. For quantum light, you need to have very specific atomic transitions, so spontaneous emission from atoms will be a single photon source. In the solid state, you can make sort of artificial atoms out of quantum dots, and this is becoming something that technology really likes, is using quantum dots as single photon emitters. Then there's also a way to create them in entangled pairs using nonlinear crystals with something called parametric down conversion. You shine a laser on the crystal, and very, very infrequently, the two photons in the laser light will combine. I'm sorry, a single photon in the laser light will break up into two separate photons that are emitted at the same time. And those are called, technically the quantum optics people like to call them the signal and the idler. I don't think the name really means anything. They're just two photons are coming out is perfectly fine. But the most important thing to know is that if I take classical light and dim it, it is not a single photon light source. So you will see many textbooks will say, if I dim the light down enough so that on average, there's only one photon like every microsecond in my device, it must be a single photon source. And the answer is actually no, because even with dim light, because photons like to bunch together, some of the time you will get two photons in your experiment, because that's the way the photon statistics work for classical sources of light. So you cannot conclude that just by dimming light you have a single photon source. And that also means a dim laser. A lot of people think that lasers mean it's quantum, but lasers create classical light, not quantum light. So we're going to start now. Why do we talk about the photoelectric effect? The main thing is that it allows us to detect single photons. So if single photons exist, the photoelectric effect says a single photon is converted to a single electron. And then that single electron can be amplified in something called a photomultiplier tube. Let me pull up my laser pointer here. It gets accelerated. There's a huge voltage between these metallic plates. It gets accelerated and hits this really hard, and 2 or 3 electrons get emitted, and they get accelerated, hit really hard, and it's like a doubling effect. And you have like 20 or so of these things, and eventually you build up a current that's big enough you can actually read it out. So the photoelectric effect is used to be able to make a detector that has single photon sensitivity. We have to amplify in order to get enough current that we can measure it with classical equipment. And then we have to be able to reset it quickly to measure the next event after you've recorded an event. And so the key thing is that because we destroy the photon in imaging it, it can only be imaged once. So this is probably the single most important property of a photon. Not that it's a particle of light, but that it can be detected once and only once, because it's destroyed when we detect it. So what are some issues that you have with photomultiplier tubes? Stray photons that are not part of your experiment can set off the photomultiplier tube. Electrons can be boiled off of the surface of a metal if it's not at 0 temperature, so stray electrons can be emitted. and then it'll look like there was a photon, but there was no photon. These dark counts are reduced if you make the detector colder. So when people try to do very precise experiments, they often will make their detectors much, much colder in order to reduce the dark counts. But they also know that the dark counts will always be there. So they just design their experiment that it can handle the dark counts, where the signal is much bigger than the noise that they're going to get in their detector. Because there's just no way of completely preventing the dark counts. So this is the first single photon source that was devised, and it's what's called a heralded single photon source. The atom that is used is calcium, and if you shine two lasers, one of 406 nanometers and one of 581 nanometers with very intense light, sometimes you can excite a two-photon transition that excites from this 1s0 state to another 1s0 state. It's an S to S transition, which is why it requires two photons. But what is really important about this is it decays via a two-stage process. It first emits a photon of 551 nanometers, and then emits a photon of 422 nanometers. So if I detect the first photon here, that's called the heralding photon, then I know within about a nanosecond to a few nanoseconds, this photon is going to come out. So the idea is I have my source here, I detect this first photon, and then I very quickly signal for my detector to become active. And then the second photon that gets emitted, I will be able to detect it, and then I can count how many of those come out. This is the way that the original single photon experiments were done. We still to this day do not have any device that I can push a button and get a single photon out. But what's nice about this one is I can be told a single photon is about to come out from the device. And that is enough to be able to handle the dark counts, because you only make your detector active during the periods where a single photon is about to come out. And this was the key to being able to develop experiments with single photons. So we now have a second worksheet, and I will keep this up. I will actually go from full screen to, whoops, smaller screen, and I will put this in the chat. We have a second worksheet now on what's called the G2 experiment. This is the experiment that you use to verify that you have single photons. And let me move this out of the way so that you can, so I'll just hold it on this for a moment. We're going to go to breakout rooms again, and we're going to work through this worksheet. This is stuff that, unless you've really done some stuff with quantum optics, you've probably never seen before. But it really has at the heart of it what a photon actually is. And we have real data we're going to use to examine exactly how we can verify that we have single photons. Okay? Any questions before we get started? And we'll do the same drill. We'll go out into the different break rooms, and I'll come by and make sure everything is working fine and answer any questions that anyone might have as well.
I will open up the breakout rooms, and they will be the same as before, same groups.
So I hope people found this very different from things that they've seen before, but still something that I think is it's quite doable by this level of students. There's no ideas in here that are complicated. Although, thank you for all of you for pointing out that the worksheets need still some work, because there are a lot of places where we could have made your life a lot easier and we did not. And I will get that fixed, and we'll have a corrected one posted and available that you can grab if you want. Did anyone have comments about things?
It worked out. I see I got the last of the numbers there. It worked out nice. I'm greater than one for alpha for first three in set one, and we're like 0.177,
Yeah.
highest is 0.64. So that made sense on the classical. So you do see what you're supposed to. It just took a little while to,
Yeah.
like you said, untangle
Yeah. We
how
could
to
have
do
made the
that
life a
math.
lot easier, so I
Yeah.
apologize for that.
No, it's all right. No, that's why
We
you
will
do
we will
these,
get
right?
it fixed. We will get it fixed. But the thing that's really I find so intriguing about this is you just looked at the double count, the coincidence counts. It doesn't look like there's a drastic difference. It's only when you actually calculate these numbers you really see there's a dramatic difference.
Hmm.
And that really I think is what makes it powerful when you work with these real numbers. And these are the ones that Aspect and Grangier did back in like 1987 or 85 when they actually did this experiment. So it's like you're working with the historic data, which I think is kind of cool as well. Okay, I'm going to go ahead and share again, and we will kind of wrap up what we're doing. If there's any further discussion about single photons, I hope you guys like this. I think it's really cool to properly see what single photons are, and this is like the experiment that lets you see it. I think it's really cool to have to understand these kinds of things about the photons. So the one thing I will now encourage you to do is not just say a photon is a particle of light. It's really much more than that. Actually, I think a much more important property is it can be measured once and only once. And now what I want to talk about is just give you a sense of what are the other things that we've been doing. This is a unit that I think you can introduce into an introductory class. I think you can do it at the high school level as well. And it is the first part of a week worth of material that is sort of the story of photons and electrons. They're sort of similar things that established what electrons are and how you can figure out that electrons are particles and get a sense of their size and other things like that. The electron story is something that the textbooks all get pretty good. So I didn't show you materials on that because that stuff is actually pretty good in all the texts. You can feel free to use what they have. Then in the way that we lay out the material, we talk a little bit about atomic physics and ultimately get into the Stern-Gerlach experiment and talk a lot about exactly how the Stern-Gerlach experiment works. It's actually quite interesting for someone who has taken a classical mechanics full year curriculum. They are actually ready to do the calculation of what a classical prediction of a Stern-Gerlach experiment is. It's not that difficult to do, and I think it really helps them understand what is so crazy about this experiment for the quantum system when you actually do the Stern-Gerlach experiment. And then what we do is once you have the notion of spin, which you get from the Stern-Gerlach experiment, you can actually go into the full formalism of two-state quantum systems. You can introduce operators on spin. You can figure out that they have commutation relations. You can figure out how to create states that have definite spin and other things like this. So that's what we would work on in the third week. Then we do have people seen Feynman's QED book? For anyone who is not, I strongly recommend that you go buy and read Feynman's QED book. It's absolutely fantastic. What he does is he uses a very simple, well, let me say it this way. If you apply Feynman's path integral approach to simple experiments with light, you end up having to use only a few paths to get all of the ideas of what's going on. And that means that you can actually do this just by talking through exactly how everything works. And you can predict very advanced experiments, things like delayed choice experiments, interaction-free experiments, and so forth, just using these very simple ideas from Feynman. And there's some of the coolest experiments in quantum mechanics. They're not these 100-year-old experiments. They are showing things like how you actually do a two-slit experiment and detect which slit the photon went through. You can do it with polarized light. They show how you can actually see something by not shining light on it, which sounds absolutely crazy, but that's what an interaction-free experiment is. There's also, I don't think, we'll cover a little bit later some of the even more advanced experiments with light. Then in the 5th week, we do a unit on quantum computers. And this is, it is actually very easy once you have this formalism here on spins. Once you have this formalism on spins in week 3, it's very easy to develop how to simulate these experiments that you just talked about in week 2 and week 4 on a quantum computer. And you can actually, you don't need to know any programming. Qiskit has a thing called the Quantum Composer. You can just select blocks that are the executables you're going to do at each point in time. And you can then use that and actually then run it on the quantum computer. You immediately get the feedback from the simulator, but you can actually run it on a quantum computer and see how well the quantum computer does for it. And you actually are doing single quantum experiments that are approximating these different experiments, and they have all of the issues that single quantum experiments have. There is noise, there are errors, there are all kinds of things. So it's really a nice thing, and it gets people excited about being able to work with quantum computers. Then in the 6th week, we still use the same sort of formalism, but we do more advanced experiments, things like neutron oscillations, atom interferometry, something that most people have probably never heard of called the Franzen interferometer. What's really cool about this is it shows how you can entangle states in time as opposed to entangling them in terms of spatial properties. You can entangle them in time. It is one of the most mind-blowing experiments. Even though I think I understand it, I still think it's black magic every time I see it. You have things like the Hong-Ou-Mandel experiment, which is an experiment that shows that 2 photons with the same frequency and same polarization that arrive at a beam splitter at the same time are identical particles. And that's really cool. It actually experimentally verifies that bosons are identical, photons are identical particles. I can't distinguish between 2 photons that have the same properties. We always say that, but this is an experiment that actually shows that. And then, of course, one of the coolest quantum experiments that are out there is LIGO. And you can also understand that using these simple ideas as well. Then we spend an entire week explaining where the canonical commutation relation is, which is commutator of x with p is I h bar. In most treatments of quantum mechanics, this is just postulated. You either postulate that the momentum is represented by minus I h bar d by dx, or you just postulate the canonical commutation relation. One or the other, you never say where it comes from, but actually you can derive it from the fact that atoms have sharp spectra in their spectral lines. And this is essentially what Heisenberg did when he discovered quantum mechanics. And so we have 2 different derivations of this. One, which is not fully rigorous derivation. There's one place where it's a little bit not quite rigorous, but it doesn't require using any ideas about matrices. And then we have one that's fully rigorous, but it uses some ideas about matrices. And then once we have that, we move on to simple harmonic oscillator. And here we bring back this idea of working with classical physics in order to understand quantum reasoning. And I actually want to show this to you. It's going to have to be relatively fast, but I actually want to show this to you if I can. Where is it? Here. And this is something you can do with this level of students. So the equations of motion for a harmonic oscillator are the time derivative of position is p over m, and the time derivative of momentum is minus m omega squared x. These are two coupled first order differential equations, but if you form a linear combination of them, you can decouple them so that the time derivative of this is proportional to this. So we just take the time derivative of that, we plug in the equations of motion, we factor out the coefficient of the p, and then this is a number, and if this is equal to that, then we have done the decoupling. And so you just set this coefficient equal to that, you find, this should be alpha squared, sorry. Oh no, when I move this over, I get alpha squared is minus m omega squared. So you find that this coefficient in front is minus I omega. So this is a differential equation anyone who's taken differential calculus can solve, because this is an exponential function. And you find it is, some constant times e to the minus I omega t. The constant is just the initial values of this A object. And you have actually two solutions, this and its complex conjugate. And I'm not going to go through the details. You can solve for x of t and p of t, and it's exactly the classical equation of motion. But what's really interesting is you can form A star A, and it's the Hamiltonian. But because one goes like e to the I omega t, the other like e to the minus I omega t, it's a constant. And now when you go to quantum, all you do is you just make everything an operator. So you just take this A, you make them all operators. We already have the canonical commutation relation. You just calculate what this is. You find the Hamiltonian, which is this, is A dagger A plus a half h bar omega. And now you can talk about harmonic oscillator. And it comes from classical mechanics. It comes from how you solve the classical mechanics problem in time. You immediately jump. And this also works for hydrogen. So you can do hydrogen in exactly the same way. So I think that's pretty cool. And I know we're running out of time, so let me just get down. So I already showed you the web page. Then what we do is angular momentum, so we can do 3D and hydrogen. And these ones that are highlighted in red, the chapters are up there. You can take a look at how we do things, their problems and stuff. We haven't developed all of the extra materials, worksheets and things like that, but it's all available there. You can take a look at it and see if you like the way that we develop this material, which is really focused on this sort of classical mechanics foundation. Okay, some additional resources. If you're not aware of it, University of Washington tutorials have a very nice one on the photoelectric effects. And that's available, I think, from Fizzport. You can get that. I have quantum mechanics courses on edX. I have a GitHub repository that has a ton of simulations on quantum mechanics. And this website, which I'll also have a QR code for, has all of my work on this. And you can explore all of that. I have a YouTube channel. It's called Quantum, the number 4, and Everyone. And it has many different kinds of videos at many different levels that cover a lot of different material. Nearly all of them come from quantum classes that I teach, but a number of them are standalone and could be used for different purposes. I've also published a lot of articles in American Journal of Physics and European Journals of Physics and some other places that discuss these ideas. You can always just ask me for advice. I love talking about quantum mechanics, so feel free to contact me. We are still developing the materials, so we're going to hope to fill out the rest of the stuff. A lot should be done by the end of next spring. And these are the two people who I'm working with on this. Leanne Dowdy is a faculty at Georgetown, and Jason Tron is our graduate student. This is my email. This is the QR
Jim,
code.
you're not sharing your screen anymore.
Oh my goodness. How did that happen? Apologies. Oh, that seems so bad.
It's a quantum effect.
I feel so silly. I don't know how I stopped sharing. I thought I was still sharing. Okay.
I think it's when you came out of the book.
Yeah. Okay. Yeah. I don't know how that happened though. In any case, just go very quickly. UW tutorials. I have courses on edX. There's a GitHub. this website, and so forth, then here's a QR code that can get you to the quantum.domain site. And I know that optics is going to have a survey, but I also have a survey. So I will I can put these also into the chat. I think you should do the optics survey first because I think theirs is a little shorter than this other survey. And if for some reason you can't get to this survey, I suspect we can email you with the link as well if you're unable to do it now. I will, though, put it in the chat so you can grab it if you need to. And that's all that I have.
Great. Thank you, Jim. Tom, do you want to do the survey or shall I?
I think it's up on the screen now.
Yes, and I'll put a link in the chat as well.
Yeah, so you can either click on the QR code or go to the website. And Chris just put the link into the chat. Thank you so much, Jim.
Oh, it's my pleasure.
Excellent workshop.
I always love talking about quantum, so you don't have to ask me twice.